Hello everyone. Today, I'm excited to present our work, ImmerseGen, agent-guided immersive world generation with alpha-textured proxies. Have you ever dreamed of diving into a 3D natural world crafted by yourself, where you can freely explore with an immersive sense of presence? Here are several scenes generated by ImmerseGen: a winter world with crisp leaves, snow-laden trees, and distant mountains, a sunset beach featuring soft dunes, rocky cliffs, and cloud reflections on calm water, and a sunlit desert with sparse shrubs in the foreground and scattered trees in the midground. One possible way to realize it is using 3D scene generation techniques. However, existing methods often lack spatial coherence, offer limited diversity or resolution, or rely on heavy 3D Gaussian reconstructions, making them impractical for real-time immersive VR applications. In this paper, our goal is to build a novel 3D scene generation framework, which enables the automatic creation of immersive environments with diverse scenery and compact representations, supporting real-time rendering on mobile VR devices while delivering photorealistic visuals and an immersive presence. The key insight is that not all scene assets require the same geometric complexity from the user's perspective, making exhaustive 3D modeling unnecessary for immersive VR. Distant objects, for example, can be effectively represented using alpha-textured proxies like billboards or alpha cards, which are much easier to synthesize. To this end, we redefine the complicated world modeling task by generating delicate alpha-textured proxy assets from low-poly templates. ImmerseGen creates panoramic 3D worlds from input prompts by generating compact alpha-textured proxies through agent-guided asset design and arrangement. Our generation pipeline alleviates the reliance on rich and complex assets while ensures diversity and realism of the scene, which is tailored for immersive VR experience. Before diving into the details, let's explain why we use generative alpha-textured assets. Here we present several 3 assets in a scene, where the left 3 are assets generated by learning-based methods, while the right 3 are assets created by professional artists. As shown, even with recent 3D generation techniques, the assets lack sufficient detail and realism for creating photorealistic natural worlds. While artist-created assets show excellent quality, they require extensive manual modeling effort. In contrast, our generated alpha-textured assets achieve much better visual fidelity than existing generated ones, with perceptual quality comparable to artistic assets when viewed from a distance. Besides, our approach also produces foreground assets with natural appearance matching high-poly artistic models. In summary, generative alpha-textured assets deliver photorealistic details without mesh decimation, while supporting flexible and efficient asset synthesis. Next, we explain how ImmerseGen created the world. First, we create a layered base world using terrain condition texturing on the retrieved base terrain, which produces 8K terrain texture and skybox, transforming the raw mesh into an immersive textured landscape. Second, we enrich the base world by adding diverse generated assets. We determine asset templates, prompts and placement with several VLM-based agents, and synthesize midground and foreground scenery with RGBA texture synthesis, which coherently adds scenery to the base world. Finally, we enhance multimodal immersion by adding dynamic effects and synthesizing ambient sounds. Now, I'll go through each stage of the pipeline in more detail. Starting from the user's text prompt, the agent retrieves a base terrain. Using the terrain depth and an expanded prompt, it generates panoramic textures for the terrain and sky to build a layered world. Let's take a closer look at the model design. We train a diffusion model to generate panoramic textures for both the terrain mesh and the sky. To ensure the panorama aligns well with the underlying geometry, we introduce 2 key components. First, a geometric adaptation module for the depth control net to reduce the train test mismatch between metric depth and relative depth. Second, a user-centric texture mapping strategy that lets the terrain sample from the panorama directly, avoiding the time-consuming backprojection step. Then, VLM-based asset agents pick foreground and midground proxies, write detailed prompts, and decide where to place them. Each asset is created with RGBA texture synthesis. For Asset Arranger, we use a semantic, grid-based analysis. We overlay a labeled grid on the panorama and mask out regions that aren't suitable for placement. Using this as a visual prompt, the agent then selects placement cells in a coarse-to-fine manner, which improves both spatial accuracy and overall semantic consistency. Once the agents decide where an asset goes and how to design it, we instantiate it by generating an RGBA texture that matches the surrounding world. To blend assets naturally, we build a context-aware, cascaded RGBA synthesis model. Given the scenery prompt from the asset designer, we first generate an alpha mask as a rough silhouette. We then inject the base world background as context and synthesize the asset's RGB texture conditioned on both the background and the mask. Since the boundaries may not perfectly match, we refine the alpha channel with a diffusion-based refinement module at last. To enhance immersion beyond static 3D visuals, we add an agent-guided multimodal enhancer for dynamic effects and ambient audio. It analyzes scene components and applies real-time shader animations for water, clouds, and rain using flow maps, noise-driven motion, and screen space effects. It also inspects the rendered panorama to retrieve matching natural soundtracks. Now, we'd like to show the screen recording of our immersive VR application. Note that we directly render the scenes on mobile devices without the need for PC streaming. Here is tranquil lake scenery, where you can hear the wind and flowing water while watching birds fly overhead and gentle waves ripple across the surface. Here is a rainy coastal scene with dynamic rain effects. Here is a desolated forest where you can walk among the trees and examine their detailed foliage up close. Next, I'll walk through the experiments we conducted to evaluate ImmerseGen. We compare ImmerseGen with 4 recent scene generation methods: InfiniGen, DreamScene 360, Wonderworld, and LayerPano 3D. To evaluate both prompt alignment and visual quality, we report clip score, clip aesthetic, and the VLM-based Q-align score. For each method, we generate scenes from diverse landscape prompts, and render videos along circular camera paths for evaluation. We then average the metrics over all frames and scenes. As shown in the table, our method achieves a competitive clip score and the best clip aesthetic and QA quality, indicating higher overall visual quality. Meanwhile, our method uses the most compact scene representation, achieving the lowest average primitive count among all methods, and delivers an average of 79 FPS on VR devices. Here we present qualitative comparisons with 4 baselines. InfiniGen, driven by limited procedural generators, often lacks diversity and may introduce incoherent objects. DreamScene 360 improves multi-view consistency via panoramic lifting, but exhibits limited scene variety and blurry artifacts due to unstable in-painting optimization and the restricted resolution of 3D Gaussians. Wonderworld, relying on outpainting, struggles to maintain cross-view consistency and can produce fragmented worlds. LayerPano 3D generates aesthetic, coherent panoramas, yet shows blur and visible seams at layer boundaries. In contrast, our agent-guided world modeling with alpha-textured proxies preserve view-consistent quality and richer immersive content across diverse environments. We conduct a user study with 50 participants to evaluate the generated scenes in VR headsets. Participants viewed randomized scenes and made forced-choice preferences on visual quality, realism and coherence, and text alignment. Our method was preferred significantly more often than the baselines. In summary, we present ImmerseGen, a framework that generates photorealistic 3D environments for immersive experiences using lightweight alpha-textured proxies. Our terrain-conditioned panoramic texturing and RGBA asset synthesis avoid dense 3D modeling, while still producing diverse, realistic scenes. VLM-based agents coordinate the entire pipeline: asset selection, prompt design, placement, and multimodal enhancements to improve immersion. Overall, ImmerseGen produces coherent worlds and maintains real-time rendering on mobile VR devices. Thanks for watching.